What's the theorem? Read the theorem. Let
G be a finite group, and let G be equal to P n M, where n greater than and equal 1, and P does not divide divide M. Then number 1, G contains a subgroup of order P for I for each I where 1 less than I less than N.
okay. Second. N, right?
Yes.
Second.
Second, every subgroup H of G of order P power I is a normal subgroup of a subgroup of order P power I plus 1 for 1 less than I less than N.
Like this. This should be minus 1, yeah?
Yes.
Okay, because until n. Yeah? So plus 1 here. So this is until n minus 1. Okay, so this is the first Sylow theorem. Okay, this is the first Sylow theorem. So thank you, Vian. You can mute. Okay, so what does it mean? Read very carefully. Let G be a finite group, so it's not infinite, finite, of order P to the n times m. So instead of writing P to the n times m, you can even write P1 to the n1, P2 to the n2, until Pk to the nk. But just say we want to concentrate on just one P. This P does not divide M because P is prime. Then G contains a subgroup of order P to the I for all I less or equal to N. Okay, so meaning G contains a subgroup of order P to the I for all the I. Okay, Wally. Every subgroup H of G of order P to the I from here is normal to subgroup of the higher order P to the I plus 1. Okay, so for easy example, look at the next example. Now, okay, this is the example that I give, the order of G. Okay, let me start with one simple one. Suppose 12. Okay, so to match into this first Sylow theorem, you can write this as 2 squared times 3, right? Okay, you can also write this, or you can write this as 3 times 4. Okay, so for this case, the P is 2. The M is 3. For this case, the P is 3. The M is 4. So this M here is just anything with the rest separately from the prime P. So it doesn't matter. Okay. After this, I will just go with P1 is 2, P2 is 3. Okay, we just do it for all. Okay, now from first Sylow theorem, then G contains a subgroup of order 2 2 from here, right? 2, 4, and from here, 3. Okay, so because it only says about the P when you multiply. So you can either multiply that, so 2 and 4, or you look at this, 3. So extending this, you can extend to P1, P2, P3, and so on. All right. And the next one says, every subgroup H of order P to the I is normal to the higher one. So if H1 is 2, H2 is 4, then H1 is normal to H2. In this case, you will see that the order is, the index is 2, but in some other cases when P is not 2, the index probably is not 2, but it's still normal by Sylow first theorem. So you can see that using Sylow first theorem, you can also show if a group is of order P, for a P group, P to the I, you can have a subnormal series, okay, because of a Sylow theorem. Because if you remember, in the last chapter, we don't prove it that way, we prove the index, but Sylow theorem says this. Okay, so next is the example in the book. We don't talk about 3 because there's no other power of 3. Okay, the next example is the order of G is 2 cubed, 3 squared, 5 to the 4, 7. Okay, so using sometimes we call it first Sylow theorem, sometimes we call it Sylow's first theorem. G has a subgroup of order 2, 4, 8, 3, 9, 5, 25, 1 to 5, 6 to 5, and 7. Okay, so this is from first Sylow theorem. You have to have this subgroup. Now, you don't know if you have a subgroup of order 6, although 6 divide. First Sylow theorem didn't say that. It just says about the power of P. Okay, and if you call it H1, H2, H3, by Sylow's first theorem also, you have this, right? You don't know whether it is normal to the whole group. It just says normal to the next one. If we call it K1, K2, so K1 is normal in K2. And 5, L1, L2, L3, L4. We also have okay. Clear? Where is your thumb? Okay. So first Sylow theorem and 2 examples. Now we go to the okay. Before we go to the other theorems, let me mention about the Sylow P subgroup. So Vian today, check. Amtinan. Where are you, Amtinan?
Yes, bro.
Just for a short while, maybe you turn on your video. Okay. Can you read the
Yes.
definition of
Okay.
Sylow P subgroup?
Okay.
Read it.
So, okay. Let G be finite group and let B be a prime divisor of G. Divisor of G.
Okay.
Okay. If B power K divides G and B power K plus 1
Does not divide.
does not divide G, then any subgroup of G of order B power K is called Sylow P subgroup. Subgroup.
This is how we write
Subgroup
Sylow
of
P
G.
subgroup of G.
Yes.
Okay.
Okay.
Okay, you can mute. So this means it's the highest power of P dividing the order. Okay, that is the Sylow P. The definition seems quite complicated, but actually it's not. Okay. Sylow. How do I keep say Sylow P subgroup of G. Okay, we use this. All right, so example, G just now is 2 cube, 3 squared, right? 3 squared, 5 to the 4, 7. Okay. Then the order of Sylow 2 of G is 8. Because it's the highest power dividing. And if you add another one, it does not divide because it's the highest. 2 to the 4. Sylow 3 is
9.
9. Sylow 5 6 to 5. And Sylow 7. Okay, so this is the definition of a Sylow P subgroup. Okay, before we go to the third Sylow theorem, a second Sylow theorem, let's go to a Cauchy theorem. We will use this at the end when we solve an example. Okay, Tan, you next. So today everyone will speak. Can you read what is a Cauchy theorem? Tan, unmute.
Wait. Find the e-learning.
Cauchy's theorem? You don't have your notes with you?
No. I go to e-learning.
E-learning.
Oh,
If I take the class, I will open the notes in my handphone because I want to see the big screen. I don't want to
oh,
share the laptop.
okay. Oh, Sylow third theorem ah. Cauchy theorem ah.
Yeah,
Uh,
page what is the page? 157.
that's 157. Okay. The Sylow theorem or
Cauchy theorem.
Cauchy 157.
157, yeah.
Oh, let G be a finite group
Let G be a finite group
and a prime that divides the order of G.
and P
A prime
prime
that divides the order of G.
that divides the order of G.
Then G has an element of order P.
Okay. Then G
Has an element of order P.
element of order P. Okay, Tan, thank you. Okay, so this gives exactly an element of order P because you don't know probably the whole big group, which one is of what order, but we have to have an element of order P. So if you have any group at all, it's easy to find a cyclic subgroup of order P by taking one element of order P because this Cauchy theorem said that that element exists. Okay, so in this group, then G has elements of order by Cauchy theorem 2, 3, 5, and 7. So that is what Cauchy theorem said. If G is a finite group and P is a prime that divides the order of G like this, 2, 3, 5, 7 divides the order. I did not multiply. You can multiply. This is few thousands. Try multiply. Anna? 8 times 9 times 6, 25 times 7. What is it?
Three one five thousand.
3, 1,
5,000.
1,000?
000.
315,000. Okay. So if I give you a question given, I don't give like this. That's too easy. So I will give you if G has this order, first question, find all possible subgroups that G must have. That is question number 1. So you will write the trivial one. So G must have a subgroup of order 1, a trivial one. And then 2, 4, 8, 3, 9, 7, and 315,000. The improper subgroup. Okay, don't forget the trivial subgroup and the improper subgroup. Okay, and list all elements order that G must have. So you will write this. Okay, next, if you found the elements in certain case, you can actually find a cyclic subgroup of order 2, 3, 5, 7 by generating this. Just generate, then you will get the cyclic subgroup. But to get subgroup of order 4 and 8, then you have to know the group. It might be cyclic, it might be not cyclic. Okay, so we can know more properties about subgroups by Sylow theorem. All right. Cauchy is another famous mathematician. You can Google Sylow, try and Google Cauchy. There's like Cauchy. We have a food named Cauchy in Malaysia. If you are Malaysian, you know there's kuih kochi. That's not the kochi. That's the kochi. Okay. Next, we have second Sylow theorem or Sylow's second theorem. Sylow's second theorem or second Sylow theorem. Okay, Iman, your turn. Read the Sylow's second theorem. Yes?
Let P1 and P2 be Sylow P subgroup of G. Then P1 and P2 are conjugate subgroup of G.
Let P1 and P2 be Sylow P subgroups of G. Then P1 and P2 are conjugate subgroups of G. Okay, can you read also what's the definition of conjugate subgroups?
Definition: if H and K are both subgroup of a finite group G, then we say H is a conjugate of K if there exists an element X of G such that H equal to X inverse Kx.
Okay, so if you have two subgroups of a group G, H is a conjugate of K or K is a conjugate of H. The same thing as before we define conjugate elements, right? A and B are conjugates. If there exists X in G such that X of K can be written as X inverse Kx. Okay, so this Sylow's second theorem says that, Iban, thank you. If you have any Sylow P subgroups of G, if you have more than one, they are conjugate. Okay, this means for one group, you can have many different Sylow P subgroups. It's not unique. It's not only one. You can have more than one. Okay, we will look at one specific example. Iman said like, why my name is erased? Then I have to talk again. Okay, Iman. Okay, example. Let G be S3. What is S3? Symmetric group of order 6. So this is 3 times 2. So from Sylow's first theorem, there are subgroups of order 2 and Cauchy's theorem, there are elements of order 2 and 3. Okay. Now, because we can write S3, the elements of S3, we can actually determine the Sylow subgroups. Okay, so S3 is 1, 1, 2, 1, 3, 2, 3, 1, 2, 3, 1, 3, 2. And you remember the subgroup lattice? You remember, right? So you have S3, then you have 1, 2, 1, 3, 2, 3, 1, 2, 3, right? And 1. Okay, so these are all subgroups of S3. Sylow first theorem said there are subgroups of order 2. Si Ham balik kampung, keluar. Just admitted. Suddenly, I'm out of the class. The funny thing about online class, if the student, any of the student is naughty, I can kick you out. Like, go out of the class, out of the door. Okay, so there are 3 Sylow 2 subgroups. Of S3. Because Sylow 2 subgroups of S3 is of order 2. 1, 2, 3. So 3 of them. Okay, there are 3 Sylow 2 subgroups of S3, namely N1 Sylow 3 subgroup of S3, namely this.
Prof.
Hmm?
How about 132?
132 is the same.
Hmm.
It's a subgroup. Okay, you generate 1, 2, 3, and you generate 1, 3, 2, they are the same. So we consider just one subgroup because they will generate 1, 1, 2, 3, 1, 3, 2. It's the same one. Okay, so you don't say there are 2 of them. This and this will give you the same. So there's only one subgroup of order 3. Okay. So there are subgroups of order 2 and 3. 3 subgroup of order 2. 1 subgroup of order 3. And by Cauchy's theorem, there are elements of order 2 and 3. Yes, order 2, order 2, order 2, order 3, order 3. Okay. Now by Sylow's second theorem, we want to show that each of these are conjugate. Okay. So Sylow's second theorem says each of those 2 are conjugate. So you have to show this, how to show these 3 are conjugate. So we call this P1, P2, P3. So P1 P2 and P3. Okay, so to show each pair are conjugates, need to find X such that Pi is X inverse Pjx for each pair Pi, Pj. Let's try with one. Let's multiply. What happens if I put X is 2, 3? Then I try to multiply X inverse P1X. X is equal to X inverse. Syiham ni lah dia balik kampung. Okay, so for a 2-cycle transposition, X is equal to X inverse. So 2, 3 inverse is 2, 3 multiplied by, I don't know, I just want to multiply. Okay, see. So the first one is this times this times this. This times this times this. 1, right? Because 2, 3 times 2, 3 is the inverse. Yeah, yeah, okay. The second one is this times this times this. Oh, I forgot to silent. Wait. Turn off. What's the answer? What's the answer? 1, 1 to 2, 2 to 3, 3 to 2, 2 to 1, 1 to 1, right? And 2, 2 to 3, 3 to 3, okay, right? And this is equal to? This is equal to? Somebody need to unmute.
Itu.
P2. Okay, so P1 and P2 are conjugates. Now you can also show P1 and P3, P2 and P3. I already give in the notes, okay? You multiply P1 by 2, 3. You get P2. You can try the others, okay? Then you can show they are all conjugate. Okay. You want to try? One more. Okay. Try multiply by 1, 3. 1, 3 times 1 times 1, 3 is 1. 1, 3, inverse, yeah? Inverse, which is 1, 3. 1, 2, 1, 3. So 1, 2, 3, 3 to 1. Okay. 1, 2, 2, 2 to 2. 2. 2 to 1, 1, 2, 3. 3, right? So this is P3. Okay. So you get P1 and P3. Another one you will show P2 and P3. So they are all conjugates, right? Okay. Next. Ahmad. Ahmad, what is your full name, Ahmad?
Ahmad Hussein
Ahmad.
Muhammad Farsi.
Ahmad Hussein.
Yes.
Ahmad. Right? Okay. You read me Sylow's third theorem.
Okay. FG
Sylow's third theorem.
FG is finite and B divides G.
Okay. If G is finite
And B divides G.
divides the order of G.
G.
The order of G. That's missing.
Missing. Okay. Then the number of Sylow B subgroups of J.
Then the number
Of Sylow B subgroup of J.
Sylow P subgroups of G
is 1 modulo B and divides the order of G.
is 1 modulo P and
Divides the order of G.
divides the order of G. Okay.
We will use the notation.
Okay. The notation of the number of Sylow P of G is this. Okay. So just now, G is S3, right? Just now, G is S3. So finite, and the order is 6, which is 2 times 3. So in this case, we have Sylow P, Sylow 2 of S3, which has order 2, Sylow 3 of S3 is order 3, okay? And Sylow 2 of S3, 1 modulo P, 1 modulo 2, and Sylow 2 of S3 divides the order of G. Okay. So this is the first case. When P is 2. When P is 2, by Sylow's third theorem, since P2 divides 6, the number of Sylow 2 subgroup of G is 1 modulo 2 and divide 6. Okay? Can you give me what is the number that divides 6? What are factors of 6? Who want to volunteer? We are still with Ahmad. Ahmad, what are factors of 6?
Factor of 6.
What are factors of 6? You know factors? What divides 6? Number
2. 2.
1,
2.
2,
3.
3,
6.
6. Okay, these are factors of 6. Which one of these is 1 modulo 2? You know modulo, right? Which one is 1 modulo 2? 1 is 1 modulo 2.
2.
2 is 0 modulo 2. Because you divide by 2, you take the remainder. That is what it means. Okay? Divide by 2, you want to find what is the remainder is 1. 2 is 0 modulo 2. Because 2 divide 2 is no remainder. 3 is
0.
1 modulo 2. 3 is 1 modulo 2. Right? If you have 2, 0 modulo 2, the remainder, yeah? Okay. What about 6? 6 is 0 modulo 2. If you want to take modulo 2 and you want it to be 1 modulo 2, meaning you have to find all odd numbers. Only odd numbers is 1 modulo 2. Okay? Even numbers, they are all 0 modulo 2. So, n Sylow 2 of S3 is 1 or 3. Okay, I will, what is it in the chat? Oh, okay, I just saw spelling your Arabic name. But since we know this is S3, just now we have shown there are 3 Sylow 2, right? If we don't know the group, if you are given just order 6, we don't know it's S3, so it's either 1 or 3. Okay, what about Sylow 3? Okay, use the same and Sylow 3 of S3 is 1 mod 3, 1 mod P, and Sylow 3 of S3 divide 6. So it is the same factors, same 6. Okay, same factors. Now you want 1 modulo 3. 1 is always 1 modulo whatever. Modulo is, you can write like this. This is always true. So 1 is always a choice. Okay. 2 is 2 modulo 3. So if K is less than P, K is K modulo 3. Like P is 5, whatever is less than 5 is that modulo 5. If it's more, then you take the remainder. Yeah? Okay. So this is modulo 3, yeah? 2 is 2 modulo 3. We want 1 modulo 3. 3 is what modulo 3? Hannah?
3 is what modulo 3?
Meaning when you divide 3 by 3, what is the remainder?
0.
0. 3 is 0 modulo 3. So you want to choose 1, right? What about 6? 0. 6 divided by 3, no remainder. So, we have only one answer for this. Okay, if you want 1 modulo 3, the number should be 1, 4, 7, 10, 13, and so on. Okay, that is all 1 modulo 3. 1, 4, and so on. Okay, so in this case, we have only one Sylow 3. Just now it's 1, 2, 3. Yeah, kan? Not 2. 1, 2, 3, and 1, 3, 2, they are similar. So the Sylow third theorem gives us this, the number of groups. Okay. Now, before I mentioned about simple group, right? A group is simple if it has no proper normal subgroup. Okay, a group is simple if it has no proper normal subgroup. There is a corollary that says that if the number of Sylow P subgroup is 1, then the Sylow subgroup is normal in the group. If n Sylow P of G is 1, then the Sylow P of G is normal in G. So this is one way to show a subgroup, if it is a Sylow P subgroup, is normal in the whole group. If you can show it's 1. Like in this case, so we know this is normal because the number is 1. Okay, but even if we don't have this theorem or corollary, we already know from before that 1, 2, 3 is normal in S3, right? We have shown this before. 1 is by you showing the coset, right and left cosets are the same. Second, because the index is 2. Third, because by Sylow theorem, the number is 1, so it's normal. Okay, so there are so many useful results from this Sylow that you can use in other applications. So when you're doing research, anything related, you want to find characteristic or properties of subgroups, don't forget to use Sylow theorem. Okay, so the next example, I've done this. Okay, next is let's try with let's see, familiar group. This is a group that we are familiar of. Okay. What is the order of G? Ain. Let Ain ask.
Order of G.
Can you write the order in terms of power of prime?
2 power of 3.
Okay. By Sylow's first theorem, D4 has subgroups of order
2, 4, and 8. 2, 4, and 8. Or 8.
By Sylow
One.
theorem is this, but the whole subgroup. Okay, 2, 4, 8, right?
8. 8.
Okay. But actually, you also have the trivial one. Okay. Okay, second theorem just saying like if you have more than 2, then you have them conjugate. By Sylow's third theorem, okay, first let me ask you, Ain, what is the order of the Sylow P subgroup of, there's only 2, right? Of D4?
2.
The order of the Sylow 2 subgroup of D4?
8.
8 is the highest. Is the highest. Okay, so this is an example because it's a P group. So for a P group, it's the Sylow P subgroup of itself. Okay, if G is a P group, then Sylow P of G is G because it's the highest power. And the order of G, if G is a P group, the order of G is this. Okay, okay. So D4 is actually the Sylow 2 subgroup of itself. All right. Okay. Next, by Sylow's third theorem, and Sylow 2 of D4 is 1 mod 2, and Sylow 2 of D4. Just want to see this. Okay. What do you have? This is like trivial case. Ain, what are factors of 8?
1, 2, 4, 8.
Which one is 1 modulo 2?
1.
Just
1
1.
modulo 2, 1.
Yeah, because this one are all even. We want odd, right? So, and Sylow 2 of D4 is 1. So, Sylow 2 of D4 is normal in,
No.
but this is actually is D4. So D4 is normal in D4 is true for all group, right? So people normally don't talk about finding this for P group because the Sylow P subgroup of a P group is the whole group. So you don't normally talk about order or P group. Okay, so at least you want to find something with the composite order P to the K times M. Okay, next. Find the number of all Sylow P of S4. Find the number of all Sylow P of S4. So let G is S4. Wally. Are you there, Wally? Today I want to call his name because I cannot see your face.
I'm here, Prof.
Your internet is not okay to show your face? Wally?
Yes, Prof.
Yes, meaning what?
I'm here. I'm hearing your voice in lecture.
Can you turn on your camera? I can see a part of your hair. You using your laptop, Wally? Little bit more?
Okay.
Ah, okay. Make sure it's not your son or relative, it's you. Okay, Wally, how are you?
I'm fine, Prof.
Okay. So you tell me what is the order of S4?
I think the order of S4 is 4 factorial.
Don't say you think. You are sure. 4
Okay, I'm
factorial,
sure.
24. Can you write 24 as product of powers of primes? So, product of powers of primes. 24 is 2
power 2 power 8.
8 is 2 cube, right? Times 3.
Okay.
Okay, so you have to write the order as product of powers. Okay. So what is the order of Sylow 2? 2. So Sylow 2, what is the highest order here? 8. And Sylow 3, what is the highest order here? 3. Okay, so by Sylow's first theorem, S4 has subgroups of order 1. 1 is not by Sylow, but 2, 4, 8, 3. Okay, 1, 2, 4, 8, 3. You got it, Oli? Everyone else, thumb. Okay, we don't know if there are subgroups of order 6. We don't know. We just know powers of primes. Okay. Now we go to Sylow third theorem. Okay, so we have to do this twice, yeah? When P is 2, and Sylow 2 of S4 is 1 mod 2. And Sylow 2 of S4 divide 24. Wally, can you give me factors of 24? Factors. 1. Unmute, Wally. Yeah.
Yes.
Give me factors of 24.
2
2.
and 3.
3.
And also
Meaning you can divide. 4.
4 is also
6. 8.
12.
12. And 24.
4. Yes.
Because this one, 1, 2, 4, 8, and then there is 3, right? So 1, 2, 3, 4, 6, 8, 12, 24. It's all the product combination. Okay. Okay, which one is 1 modulo 2? Which one is 1 modulo 2? I said the odd ones, right? Not the even one. 1, 3. So 1 or 3. Okay? 1 or 3. I know the answer is 3, not 1. Because Sylow 2 of S3 is order 8. In S4, there are 3 subgroups of order 8 in S4. It's not 1, there are 3. Find them. This is exercise 10, actually. Next assignment, number 3. I'm not gonna give you. So there is no element of order 8 in S4. You see? In S4, what is the page? S4, we have chapter 4, I think. When we do permutation, okay, you can see in the example, chapter 4 at the end, all elements of S4, 24 of them. You will see that in S4, the form of elements are AB. A is the identity, right? Identity. AB, ABC, ABCD, ABCD. These are the forms of elements in S4, right? Right? So 1 cycle, 2 cycle, 3 cycle, 4 cycle, and then 2 cycle. Do you have element of order 8? This order 1, this order 2, this order 3, this order 4, this order 2. So there is no cyclic subgroup of order 8. There is no cyclic subgroup of order 8. Okay? So the subgroups that order 8 in S4 is not cyclic. You remember last time I said there are 5 subgroups of order 8. One is the cyclic, right? Z8. Another one is Z2 plus Z4, Z2 plus Z2 plus Z2, quaternion and dihedral. Okay, so it's not cyclic, but there are 3 subgroups of order 8 in S4. You have to find them. So meaning, suppose these are elements of the subgroups of order 8. This is already the identity. Okay, some of them are, because this is order 8, so some of them are orders. 1 is the identity, some of order 2, some of order 4. So you, right now it's easy. This one is Google, you can get the subgroup, but I'm not gonna give it. Okay, so 3, yeah? I haven't finished. The next one is Sylow 3, right? Sylow 3. Sylow 3. Right? So just now we have 1, 2, 3, 4, 6, 8, 12, 24. Now which one is 1 mod 3? 1 is 1 mod 3, 2 is 2 mod 3, 0 mod 3, 4 is 1 mod 3, 0 mod 3, 2 mod 3, 0 mod 3, 0 mod 3. So 1 or and where is my Sylow 3? Sylow 3 of S4, the order is 3, right? Right? So the answer is 1 or 4. How many Sylow 3 subgroups of order 3 in S4? Must be 4, cannot be just 1, right? Because you can generate all the elements of order 3, this. Then you get all the subgroups of order 3. It has to be cyclic because it's prime. Okay, so there are 4 cyclic subgroups of order 3 in S4. Okay. Three. I give the answer there already. I don't remember I give the answer. I give you 1, 2, 3, 4, and 1, 2, 3, 4 generate, meaning it's multiple of those two. Okay? But I want to see you write 8 of them, 8 elements. Okay? And I already give the Sylow 3 subgroup of S4. Just generate 1, 2, 3, 1, 2, 4, 1, 3, 4, 2, 3, 4. So you'll have 4. Okay. Okay, let's do this one example. Decide whether a group of order 40 is simple or not. Okay. This is not English simple. This is group theory simple. Remember, a group is simple if it has no proper, non-trivial, normal subgroup. So trying to decide whether there is a normal subgroup or not. Okay. Okay, so let G be 40. Let me see. I have Corvian, Antinantan, Iman, Lava. Lava. It's your turn. Okay. Can you write 40 as product of powers of primes?
Yes. 2 cube times 5.
It's 8 times 5, right? So 2 cubed times 5. Then what is the order of the Sylow subgroup of G? The Sylow 2 subgroup of G of order?
8.
8, the highest one. The Sylow 5 subgroup of G of order?
5.
5. Okay. By Sylow's first theorem, G has subgroups of order Lava 1, 2,
4, 5,
4,
5,
8, 5, and the whole thing, right? Now, we want to see if any of this is normal or not. but we don't know. Now by Sylow's third theorem. When P is 2, I don't know which one to choose, but I just show. When P is 2 and Sylow 2 of G is 1 mod 2 and Sylow 2 of G divides 40. Okay, Lava, give me all factors of 40.
1, 2, 4, 5, 8,
1, 2, 4, 5,
8, and 40.
8, 10.
40.
What about 20?
Yes, 20 and 40.
What happens if you miss one factor? What happens if you miss one factor? It's very dangerous. So make sure you know your factors. Okay, so which one is 1 mod 2? 1,
5.
5 only, right? Okay, now when P is 5 and Sylow 5 of G is 1 mod 5 and Sylow 5 of G divides 40. So, and Sylow 5 of G. So which one of this is 1 mod 5? 1, 2 mod 5 is 2, 4, 0, 3, 0, 0, 0. Right? So, Sylow 5 of G is normal in G. Okay, what's the answer? So, is G simple or not? G is not simple. Because G has a proper, normal, non-trivial subgroup. Okay. If it's okay, give a thumb up. Okay or not? Amtinan said okay. Tan? Okay? Iman?
How about Sylow 2G? Sylow 2G?
Hmm?
Sylow 5G has a triple non-trivial normal subgroup. How about Sylow 2G and Sylow 2G?
I cannot hear you.
How
What
about Sylow 2G? P equal to 2, P equal to 2. P equal to 2 have 2 value, right?
This one?
How about have any meaning at there 1 and 5?
This one we don't know. We don't need to know. Once we know there is one here, then we have a normal subgroup.
Oh.
This one, because we don't know what G is. So this has nothing. Doesn't give anything. So we just leave it. This is just a possibility. Okay? Okay, I will leave the last example for you to read through. Try to understand for Wednesday. Okay, there is one more. I want you to try and understand. Okay, last example with order 99. Okay, and number 6, exercise 10. Exercise 10, number 6. Next class, we will go over it, but I want to see whether you can do it. Okay. Okay, so I will stop here. Any question? All right. So on Wednesday, we should start our class at 3, 3 to maybe 4:30. Okay.